All right, we are going to continue with our polar graphs by simply summarizing everything that you were able to find from the Polar Graphs project. I know some of you, well, I know that all of you did the first half and you all have the same information if you did it correctly, but you at least researched the same graphs there, and then you had a little bit of freedom in choosing which graphs to pick for the second half. So this is just a summary, just to be sure that everyone has kind of the basic polar equations that I want you to know. We'll go over them. We'll go over how different variables within the equation will affect the graph. I know some of you may have researched ones that are outside of the ones we're going to go over today, which is absolutely fine. But these are the ones that I want to make sure that we all understand and we all know how they work. Okay, so we're going to go ahead and get started on Rose curves. So Rose curves are the ones that are in the form r equals a times sine of n theta, or r equals a times cosine of n theta. Okay, so we have two things. Remember that these are polar graphs, so r and theta, you want to keep those in there, but anything else that's in there, for example, the a value and the n value are going to change, are going to result in some sort of transformation on the curve. So there are two things. So first, start with A. A is going to affect the length of each petal, so how far out they go from the center. And then the value of n will depend on whether it's even or if it's odd. Okay, so it's not simply how many petals there are, which in some cases that's the case, but in particular when n is even, right, these are the two that are on the left here. What we have here is an example of r equals a times cosine of 2 theta, and r equals a times sine of 4 theta. So in each of these cases, you can probably see, we're focusing on the two on the left, you can see that there is symmetry with respect to the x-axis, the y-axis, and the pole. Okay, so there's symmetry in 3 different ways. And then secondly, n, when it's even, 2 times whatever that number n is, gives you the number of quote-unquote petals that the curve will have. Okay, so it has 2n petals. All right, and the two graphs that are on the right, we have r equals a times cosine n theta, r equals a times sine of n theta, where n equals 3 for the cosine graph and n equals 5 for the sine graph. Now, the symmetry is going to be different depending on whether you're looking at cosine or if you're looking at sine. So for the graph with cosine, we're going to have symmetry with respect to the x-axis. Okay, and then the number of petals is simply going to correspond to whatever n is. So in this case, n is 3, so there are 3 petals. Okay, and then for r equals a times sine of n theta, this is going to have symmetry with respect to the y-axis. And again, n is going to directly correspond to the number of petals. So this will also have n number of petals as well. Okay, so that's the basic summary of Rose curves. The second group of polar graphs that I'd like to summarize for us, the way that we pronounce this is limison. This is a French word. So for those of you who are or who have taken French before, this C with a little accent at the bottom that looks kind of like a hook, that makes the C instead of a hard C and makes it an S sound. So you would pronounce it limison. Okay, so this is the group of graphs that are of the form r equals a plus or minus b sine theta and r equals a plus or minus b cosine theta. Now note that when we use this form, we're specifically stating that A is greater than 0 and B is greater than 0. So that's why we say plus or minus. That way we can keep B as being positive. Okay, now the sine theta version of the equation is going to have symmetry with respect to the y-axis, whereas the cosine version will have symmetry with respect to the x-axis. Okay, and then the a and the b values, these will tell you how far along the graph will extend. So for example, a plus b will tell you the distance that the limicon is going to go along the positive axis, and then a minus b will tell you the distance that it will go along the negative axis. And now depending on how a and b are related to each other, there are 4 different what we call types of limicons. So we have the 4 here. So the first one, this is where a over b is less than 1. If it helps you, you can think of this as a being less than b, right? A has to be smaller than b in order for that fraction to be less than 1. Or you can think of it as multiplying both sides by b to get a is less than b. Okay, this is what we call a limicon with an inner loop. Okay, so anytime you see a graph of a limicon and you see that it loops back inside of itself, that means that a is less than b, or a over b is less than 1. Okay, the second one, this is where a over b is exactly equal to 1, which means a and b are equal to each other. Right, again, you can multiply both sides by b, you would get a equals b, right? So when those two are equal to each other, then we have what we call a cardioid. Okay, it's more of a heart shape, so instead of actually looping, it just goes right to 0. It doesn't curve, it just goes right onto 0, and then very abruptly goes back out again to finish off the rest of the limicon. Okay, so that's a cardioid. Okay, now the next one, this is the reason why we use a over b instead of just saying a is less than b, a is equal to b, because the next one is when a over b is between 1 and 2. Okay, when a over b is between 1 and 2. So this is what we call a dimpled limicon. So it's exactly what you think of when you're thinking of what a dimple is, for example, on someone's face. It just goes in just ever so slightly, but then curves right back out. Okay, and then the last one is when a over b is greater than or equal to 2. Then we have what we call a convex limicon. So if you remember the difference between something being concave versus being convex, concave means that whatever your graph is, whatever your shape is, it kind of goes back into itself, right? So the first 3 do go kind of back into itself in some way, but a convex limicon is when instead of actually going back into itself, it just kind of flattens and then curves back around. All right, so that is it for limicon, for the summary. Our next group of polar graphs are lemniscates. So there are, again, 2 versions, one sine, one is cosine. So r equals a square root of sine of 2 theta, and r equals a times the square root of cosine 2 theta. You may also see this in the form r squared equals a squared sine 2 theta. That's fine as well. I'm just trying to keep it consistent so they're all r equals an equation. Okay. So a is going to represent the length of each petal. you will notice that we're talking about petals, so kind of relates to rose curves. They are similar in a certain way, particularly because we do have that sine of 2 theta, cosine of 2 theta, but it's always 2 in front and not just any value of n. Whereas with rose curves, it's sine of n theta, cosine n theta, and so n could be anything. Okay, so for the first one with sine, our graph is going to look like this. And with cosine, our graph is going to look like this. So really the only thing that's going to change here is the value of A, and that will just change how long the petal is. All right, so in terms of the way it's facing, it's always going to be the same. Okay, so for the sine theta version of the lemniscate, this has symmetry with respect to the pole and to the line y equals x. And for the cosine version of this has symmetry with respect to the x-axis, with respect to the y-axis, and with respect to the pole. Okay, and then the last group of polar graphs that I'd like to summarize are what we call the spiral of Archimedes. All right, so this is the one where you don't have sine, you don't have cosine in the equation itself. It's just r equals b times theta. R equals b times theta. Okay, now b controls the distance between successive turns. So if you have a smaller b value, that means you'll have a tighter spiral. If you have a larger b value, that means you're going to have a looser spiral. Okay, and then depending on whether theta is positive or negative, you'll know the two different versions of the graphs. Now, note that in both of these graphs, I know they start in the same place, but they somehow look like they're maybe going different directions, but if you follow it very carefully, both of them are actually moving counterclockwise, right? So it's not that it changes the direction in which the spiral is turning. The spiral is still going counterclockwise in both cases. But if you look very closely at where they start, look at the first quadrant in which they enter. So when theta is positive, it starts in the first quadrant, right? And then starts spiraling from there. Whereas in the second case, where theta is negative, when it starts spiraling, it starts in the third quadrant and then starts spiraling out from there. Okay, so you can think of it as going towards the positive direction versus going towards the negative direction in terms of which quadrant, right? So when theta is positive, you start off in quadrant 1 where everything's always positive, right? So you can think of it that way, but do not think of it as it's one's going counterclockwise, one's going clockwise, because they're actually, in fact, both going counterclockwise. Okay, and if B were 2 theta versus 5 theta, you would know that if it were 2 theta, then this spiral would be much tighter. If it were 5 theta, then the same spiral would just be loosened up and it would coil a lot slower, right? It would be much looser. All right, and that is the summary of the groups of polar graphs that I would like you to know. And that's all we have for today.